Chuck,
Hey,
time for things you thought you knew.
yes, and in my case, things I know I didn't know.
That's a very important state of mind, to know what you don't know. Because if you didn't know what you didn't know, that's just abject ignorance. I mean there's
That
no
is true. That second part is sad. What you just
sad,
said.
exactly.
That's sad. Ooh, that's
sad
that's
ignorance.
terrible. That's sad ignorance, man.
All right, so Chuck, how do you know how big something is?
Yeah, measure it.
You measure it, right? So you pull out a
Yeah.
ruler. Let's say it's a table, and you measure it. Okay. So there are two things working against you on that. One of them is, how close together are the hash lines on the ruler,
Right.
right? Because if your table ends up between two of them, then you don't know how long your table is. If you're going to report to me, you can only say it's between here and there, and venture a guess to where it is from one marker to the next.
Okay.
That's kind of like half, maybe. What you'll give me a guess, fine, but you won't know exactly because you don't have the metrics to determine that. Okay?
Right.
No,
It's like
watch.
measuring in hands. He's 7 hands tall. Really? That's all?
Well, hands is actually a specific measurement. I mean, I think the hand is 4 inches.
Oh, really?
The width of your hand. Yeah.
Look at that. I see. Now I just learned something there.
Horse heights are measured in hands.
In hands, right. I knew that the horses were measured in hands, but I didn't know that the hand had an actual unit.
It's around 4 inches. Don't quote
okay.
me on that. But
All
yeah,
right, that's
yeah,
cool.
yeah. Okay,
That's cool.
okay.
Good stuff.
Okay. So even if you had the precision to measure the length of the table, if you go down under a microscope, like a really good microscope, like an electron microscope, that's the kind of microscopes where you see all of the hairs on the bugs, and you see the eyeballs of the fly. Those kind of microscopes. If you do that, you'll see that the edge of the table is not smooth. It's actually got texture. So which feature of the texture are you going to measure it to and then report back to me the width of the table?
Well, okay.
What happens is at some point you just give up and say, Neil,
I can't.
you're
You can't
annoying
measure
me.
anything. Right.
you can't measure anything unless you
can't
just
measure anything.
agree. You just agree how you're going to take the measurement, and then you're good with that. Well, if you have that problem with solid objects, imagine the challenge measuring the extent of gaseous objects. Just imagine that. Okay.
Yes. I believe you measure that and how bad it smells.
Not all gas came out of your rear end, okay, in this world. Just saying. So you can ask, how high up does the atmosphere go? Well, so you ascend and you say, is there a sign that says you are now leaving Earth's atmosphere? No. No. The atmosphere gets continually thinner.
Right.
And you know this because as you ascend a mountain, the air pressure drops. It's harder for you to breathe. You can still breathe, but just every lung's worth of air has less oxygen in it. Okay? That's your evidence that the air pressure is getting lower and lower and lower.
Should have never smoked, man.
Okay.
God, this is killing me.
This continues. You go into an airplane. Airplanes are pressurized,
Right.
which means they put air in there. Otherwise, you would suffocate if you roll down the windows. All right? So those oxygen masks, those are there in case the airplane loses pressure. And you're breathing very low density air, has hardly any oxygen in it. Right. So you breathe through the mask. That's all. Okay? By the way, you could hold your breath until you did this. I mean, you're not going to die immediately. You have to fight for them. It's just air. Okay?
Right.
You've held breath holding contests for longer than the time it'll take you to reach for one of these yellow masks.
Little cups, right? And remember,
okay.
people, always put your own mask on first before you try to put the mask on that of a child. So, which, by the way, no one had to tell me. Okay. Like when I heard that, I was just like, and what else would I have done? Okay.
Chuck was first out of the box on that one.
Exactly. I was like, this kid ain't bringing nothing to the table. Really? I might just let the kid pass out just so I can get some rest.
Oh, that was the noisy kid. You're not giving him the oxygen.
Exactly. Wait, let's not be so quick there, Mom. That kid is looking real peaceful right now.
Jack,
All right.
that's cold. All right. Oh, by the way, it's also literally cold as you leave Earth's surface because you're farther away from the heat point of the heat generating point, which is, that's another, scratch that. That's
Whole nother explainer.
Whole nother. Okay. So as you ascend, the air just simply gets thinner and thinner and thinner.
Okay.
There is no spot where you say it ends here and it's space. No, there isn't. So you just have to agree on what that altitude will be. Pick a thing and then just, you good with that? I'm good with that. Fine. Put it in the books. Move on to the next problem. Okay.
Okay.
So there's a guy in the 1960s named Karman.
All right.
Okay? He was a Hungarian, I think, but worked in the United States. And he said there must be an altitude above which the atmosphere is no longer scattering sunlight above your head so that it's no longer sky blue. The blue goes away and then you just see stars in broad daylight.
Oh, wow.
That's an interesting threshold, right?
That is.
And that's fair. There'll still be air molecules there, just not enough to scatter because that's how you get a blue sky. It scatters the blue of sunlight, and now the sky is glowing and you can't see the night sky. You can't see stars in the daytime sky. Gotcha. So, because it's daytime. However, if you ascend high enough in the atmosphere, there's a point where there aren't many molecules above you. Bada bing, the sun is still there, but you can see stars in addition to our own star in the sky. So that's called the Karman Line. And ever since the early 60s, the Karman Line has been the functional definition of a transition into space, whether or not you were in Earth orbit.
Interesting.
Our first astronaut, Alan Shepard, went up in 1961. He went into suborbital, was fished out of the Atlantic, okay, and he went high enough to go above the Karman Line. So that counted, and so that's sort of our astronaut threshold. Karman himself, however, knew that the atmosphere is not some rigid thing, it's gas.
Right.
And sometimes it heats up, sometimes it cools down, so it will expand, it will shrink. And so the Karman Line is not itself a definite thing. But if you're going to look for it, you'd find it anywhere between 80, 85, and 100 kilometers. Okay, that would convert to 53 to 62 miles up. Somewhere in there. Okay, and so to say, did you hit this exact point or not? That's like arguing, which edge of the table are you using to give me the length of the table? Except worse because it's gas.
Right.
So, point is, the atmosphere continues out for thousands of miles.
Oh no.
Yeah, in fact,
wow.
The International Space Station, which is 250 miles up.
Right.
How much higher than the 62-mile Karman Line is? It's 4 times higher than the Karman Line. The International Space Station is huge. It's like the size of a football field moving through the air. There's enough atmospheric molecules up there to hit the solar panels and the physical body to drop it to lower orbits than you had originally intended. So every now and then, the space station has to boost itself up back to its original target orbit because of the air molecules that hit it.
That's insane.
Yes. And that's 250 miles up. So there is no edge. And if you're going to ask me, what is the diameter of the sun? You could look this up in a book. You could look this up. The diameter of the sun, it'll give it to you. And you say, well, wait a minute. The sun is made of gas. So how precisely are you measuring that? You take a ruler and do that? Not only that, you can say, in what wavelength of light did you measure the diameter of the sun? Do you know different wavelengths of light emanate from different locations within the depth of the sun? If you're like Geordi on Star Trek Next Generations, and you look at the sun in ultraviolet light, it has a different dimension from what it has if you look at it in visible light and if you look at it in infrared light. Then if you look at it in X-rays, all different dimensions. In fact, the solar corona, the thing that's glowing outside of the moon when you see the solar eclipse, that's called the corona, which is Latin for crown, so sensibly, right? So if you looked at that with X-rays, that's the size of the sun. Forget the down on the sun's surface, gaseous surface. X-rays, the corona is ablaze with light. And you're going to say the sun is huge. So I just want to put it out there that the dimensions of things is really just something you just have to agree to in advance. And then you all agree, you put it in the book, and then you move on. So the diameter of the sun is the diameter it shows to us using yellow light, which is right in the middle of the visible spectrum. That's the number you're going to read in the book. But they don't tell you that, but I'm telling you that.
I'm glad you did, because it's good to know they've been lying to me all this time.
Oh, by the way, and you can think of other definitions of space. I got one for you. You ready? So airplanes use fuel. It's called aviation fuel. There's a word for it. I forgot what. But anyway, it uses fuel. So fuel, our common understanding of fuel is you burn it and then you get energy. But what does it mean to burn it? It means it gets attached to the oxygen molecule, creates a third other product, right? There's that molecule, the oxygen molecule. They merge and make this other molecule, and it's exothermic. Energy gets generated. Okay. That's how cars work. That's how airplanes work. Well, where's it getting its oxygen from? The atmosphere. Okay? Wait a minute. But if you're a rocket and you're going to where there is no oxygen, where there's not much oxygen, you got to bring your own oxidizer. You can't depend on the atmosphere. So you could say you enter space at an altitude where an airplane can't get enough oxygen to fly anymore. And it just drops out of the sky. That's an interesting threshold. You could have done it that way. Because above that, you need a rocket. And we all know rockets equal space. Okay?
There you go.
I can think of 10 other ways you might define it. But I'm just saying, just numbers and measurements of things they're not written in tablets. You have to agree on what it is you're trying to measure, write down that number, and then move on.
There you go. Measurements not written in tablets, only commandments.
All right, that's all we got time for.
All right.
Yeah, that's a crazy subject, but I have to put it out there.
No, that's very cool.
And when you hear people arguing over the Karman line, just sit back and chuckle and say, the Karman line is an idea more than is an actual place within Earth's atmosphere.
Well, if I ever get into an argument about the Karman line, my answer will be, so how big is the sun?
And also the 100-kilometer Karman line, did you really think the atmosphere is layered into evenly divisible numbers in kilometers? Did you really think that's the case? If you look up Karman line, it's 100 kilometers. Yeah, right. The Earth is like tight with the metric people, right? It's like, no, 100 is well above whatever Karman was talking about. But if you want to round it up, you round it up to 100 kilometers, and that's the definition. Fine. Okay? And the American definition is lower than that. We're like at 85 kilometers up. We have a lower definition than Europe and the rest of the world do.
Oh, well, that's because, we want to be able to say we went to space.
We want to be able to say that Alan Shepard went into space.
Went to space.
Correct.
Exactly.
Right.
We're the first people to do it,
Right.
It's just like we put a spire on top of the Freedom Tower, and it's like now the tallest building in the country.
Exactly. Yeah. All right, Chuck, we got to end it there. But if you hang on, when we return, we'll go into another segment of doing some explaining. Stuff you thought you knew. That's what this is all about when we return. So, Chuck, we're back.
Okay.
For another explainer.
All right.
This one, did we talk about this before? I have a bad memory for what I've been talking about. But I'm going to do it anyway, and if it's not, we'll just do it again. Here it is. You ready?
Okay. What is
Okay.
it?
So there's an interesting difference between being an astrophysicist and being a photographer. Okay?
Okay.
Here's the difference.
A college education? I mean, I'm trying to.
Okay, here's the difference. We know that when you have an object and you heat it and its temperature rises, it actually radiates energy. Okay? If it's very cold, it'll radiate radio waves and microwaves. In fact, the whole universe is 3 degrees absolute zero, 3 degrees above absolute zero. Very cold. At that temperature, microwaves get emitted. So the universe is a source of microwaves upon us because of that leftover temperature from the Big Bang. Heat anything more, so I don't care what it is, heat it some more, and then the energy it'll start giving us will start shifting in the spectrum, and then it'll start giving us infrared energy. Okay? You can't see it, it's not glowing visibly yet, but if we have sensors that are not our eyes to detect infrared, you know what it's called?
No.
Touch. Okay, you can touch it. Okay.
Heat, right? Yeah.
Yeah,
So
yeah.
there
If
you
it's
go.
if it's warm, you can detect low level infrared all the way up to high level infrared just by getting near it, and you can feel the energy, or you can touch it and you can feel the temperature. Okay.
Okay.
So Chuck, it gets a little warmer than infrared. Now it begins to glow red, and so now it's giving you energy. It's giving you photons in the visible part of the spectrum. Say, hey, that's hot. That's glowing red hot.
Right.
Okay. But I know that you can keep making the temperature higher. It'll still glow, but now it's going to glow white hot and then glow blue hot. And the blue hot is the hottest of the glowing temperatures. But we don't experience that in everyday life. So
Nobody says blue hot anything.
anything. They don't say that anything. Plus, ice and icebergs have this blue tone to them. So psychologically, it all feels different. But here's what's interesting, okay? When we transitioned from incandescent bulbs, the old-fashioned Edison light bulb, to LEDs, okay? Ask yourself, why would a light bulb giving you visible light ever get hot? Because it's glowing white hot, but it's also still giving off infrared. Okay? So, but wait a minute, I have a light bulb so that I can see. So the 100-watt light bulb, or whatever the wattage you bought, it turns out most of that energy is coming out in the infrared.
Yes.
It's
Which
a
is-
waste.
Which is why they would always say on the package, it would say, wait for whatever, however long before changing the light bulb. Because so many people be like the light bulb would blow out. They would go get another light bulb, come back, go to change it, and burn their hands. That's how hot the bulb was.
It's a complete waste of everybody's energy. The fact that we had light bulbs that was giving us infrared.
Wow.
So, the brilliant thing about LEDs, and let me remind you, LEDs are of this next generation interior lighting. We couldn't do it until we had all 3 colors of LEDs. We had red LEDs.
Right.
We had green LEDs. We didn't have blue.
Blue.
And that would, once we got blue, we'd have RGB. You can combine them, and RGB combined in light. Doesn't work this way in paint. Don't tell your artist friends this. You combine RGB with light, and you get white light. The thing about LEDs is they're not glowing. They're not glowing from heat.
It's actual white light.
It's actual light coming out at those frequencies, at the red frequency, at the green frequency, at the blue frequency. Your eye merges them and you see it as white light. There is no energy coming out in the infrared or anywhere else. That's right. So that's why you could have a 3-watt
yes,
LED bulb that just kicks ass against a 60-watt, or however many, 5 watts, whatever, against a 60-watt Edison bulb, regular old-fashioned bulb, because most of that Edison energy is coming out in infrared, and none of that energy is coming out in infrared for the LED. It's all in the visible part of the spectrum.
I don't know why we didn't do this one so much earlier, because 2 things. And it's so exciting that you just actually did everything you just did and related it to light bulbs. 1, people went crazy when we said we were going to transition to all LED light bulbs, and they did it because President Blackula said that we should actually move to all LED light bulbs. And people were like, now the government's trying to tell you what kind of light bulb you can have. No, I swear to God, it's my God-given right to have me a regular incandescent light bulb. That's America. And so people lost their minds.
Who's Chuck's imitation of America?
They lost their minds.
They lost their minds.
And
okay.
what you are saying is, 1, it's more efficient because it is exactly what it is, which is
so it's energy efficient by a factor of 10. Okay.
Right? And then the other thing you said was that is why you see on the box it's whatever many watts instead of like your 200-watt bulb or whatever. It's like, it says they do lumens now.
Yeah, you can't use watts because you know what watts are. Watts is not the measure of the brightness of anything.
Right.
Watts is the measure of how much energy, the rate at which it's consuming energy.
Exactly.
And since we all had the same light bulbs, you could compare watts and say that one is, twice whatever. You had some sense of that.
Right.
But really with light bulbs, it should have always been measured in lumens. In fact, in Europe, I think they always measured it in lumens. Yeah. So you're after lumens here. You're not after wattage. Okay? So this is a maturity of the American population.
Yeah, this is the best reason for you people to go out and get LED lights. I mean, for me, I got into this because it's great for the environment. If we all did it, we would really lessen our carbon footprint for the entire nation. But the fact is, here's why you should do it. You save money. You just proved how much more efficient it is. You
save your own damn money.
Save your
Correct.
Own damn
Even if you don't care about the environment, care about your own damn wallet.
There you
right?
go.
So, and that's why you can go up to any LED bulb and it's not hot. It'll never be hot. It's not about being hot.
Man, that's great.
And here these people say, Earth is flat and I don't like science and other. The person who discovered the blue LED got a Nobel Prize for that because the moment that got discovered, it blew open the entire lighting industry. Because now you can make white light. In fact, you can make any color light. That's why you can get LED controllers where the light itself has an RGB diodes in them, and you can just control the ratios of those and get any color you want. Mm-hmm. And so you can. The Empire State Building is lit by these things, okay? And it's the intensity of the color is very real and it's very in the moment. So just thought I'd tell you that.
That's super cool. Well, listen. White light was what we were striving for, but always remember, only black light can make your dorm room look cool.
Oh, by the way, so black light, just to be clear, is an ultraviolet light. But the part of it you see is the violet that's just kicking into the red, orange, yellow, green, blue, violet part of the spectrum. You can see that, but that's not why you have it in your dorm room. You have it because the ultraviolet light interacts with the pigment in the pictures on your wall, the posters, and it forces the pigment to glow. Okay? And it's called phosphorescence, right? And so that high energy light that you can't see, the pigment can't see, it absorbs it, and then gives it back to you in visible light, and it looks like the paintings are glowing. So in a sense, it is black light. It is light that you can't see.
Nice.
Yeah.
All right. Well, this was great.
You got it, Chuck. So next time you walk by an LED, just pause and say, "Thank you, science."
There you go. Just say that anyway.
Say that anyway.
Just say that anyway.
Wake up in the morning, take a deep breath. Thank you,
Thank
science.
you, science.
I should tweet that. I'm going to do that. Let me see if I
Exactly.
can start a movement. So, Chuck, that's the end of this segment. When we come back, we're going to do another one of these, Chuck.
All right. Sounds
Okay,
good.
you got it in you to listen?
I got
to
it in me. Let's
hear
do
out?
it.
Okay, all right. We'll be right back. Chuck,
Hey, Neil.
I'm back with another sort of stuff you thought you knew.
Right on.
This one might be something you didn't even know you didn't know. How about
Okay.
that? There's some of those are out there too, right? So no one told me this. I discovered this on my own. That if for those of you who have ridden airplanes, I know some people have never been in an airplane. I highly recommend it. It's quite a marvel of engineering and physics and and aerodynamics.
Or you can watch YouTube.
Okay. Okay. So if you could save up, if you've never been on an airplane, find a place to fly to and just check it out. It's quite a marvel. And I marvel at it every day, even though we've been doing it for more than 100 years. So I noticed when I pull down the shades, and I can't see outside, and I look at this drink, and the water level is completely horizontal.
Okay.
All right, that means we're just there. We're not, accelerating or banking or turning. Okay, it's just there. And it stays that way the entire trip.
Right.
Now, I know the plane has got to make some turns when it comes near. I know it's got to do this at some point.
Right. Yes.
If it does that, I would expect the water level to tilt within the glass. I'd expect me to lean in one way or another, the way it would happen in a car. If you make a left turn in a car, your body leans to the right, okay? Because you actually want to keep going in a straight line, but the car is curving in front of you. So it feels like you're getting pushed to the right, but really you're just going in you want to go in a straight line. The car won't let you. And you're getting pushed against the door. Okay, or you turn left or right, whichever, or someone's sitting next to you, your shoulders will touch. All right, no longer does that happen on an airplane. So what I did was, let me try this with the shade up. I do it with the shade up. I look out this window, I see sky. I look out across the plane, I see the ground. This sucker is banking, and yet the water on my table is completely flat.
Okay.
So, there's only one thing that can be happening here, because I don't think humans have this ability. The computer is flying the airplane, and you program into the computer such that the radius of the turn and the speed at which you're going requires that the plane be at a certain banking angle so that all the centrifugal forces combine with gravity so that you don't even know you're banking this turn. In other words, the urge to fall into the middle of the circle gets completely balanced with the centrifugal force to send you out of the circle so that the gravity vector still goes directly to the bottom of the glass and to your rump into the chair. And you don't even know the plane is turning. Those three numbers, if you choose them correctly, you can have them conspire so that you would never know the plane was ever turning at any time.
Well, clearly you have never been on Spirit Airlines.
Top. The pilot's in there.
They don't even use the joystick. They use an actual steering wheel.
I'm sure it's a fine airline where they have fully trained pilots.
Okay.
But the precision necessary to do that reliably, to do that without the judgment of the pilot, is that takes a computer. And if you look at old movies where they show people on airplanes and the airplane is turning, you'll see people sort of leaning to the one side or the other. Right. That is no longer a thing in airplanes.
And you know what you just reminded me of when you're talking about going back is old episodes of Star Trek, the first Star Trek, where the entire crew would go to the left, and then they go to the
They
right.
leaned. Hold on. And they'd all be instructed to do this, right?
Right.
So they take the camera and tip the camera.
And
right?
they tipped the camera, and they would all do that to make it look like they were banking, and they were in space. So
So if you bank a turn properly, you never feel that effect. And by the way, we've talked about this with NASCAR. All right, what the banked turn in a racetrack, there is a speed with which you can drive your car so that you never have to touch the steering wheel, and the car will make a complete turn on that bank and end up going back the other way.
right.
And that speed is one where you will not feel like you're leaning to the left or the right.
Because the road is turning for you.
The road is turning the car for you. Correct. And at the right speed, you'll feel the gravity vector doing whatever it was doing before you entered that turn. It's the same physics principle at work there. So I just thought I'd put that out there. Just a little discovery I made. I haven't checked with anybody who did it and when it started, but I began noticing it. And you should notice it too. Just check it out. There could be sky here and brown down there, and you don't even notice it unless you look out the damn window.
Yeah.
Just saying.
Well, I fly Spirit, so I notice it all the time.
It's tough. Wait, one last thing. If you are in space, there is no banking of turns.
Yes.
Okay.
Right.
Well, I'll tell you why. Because so on a track, the thing that's turning the car for you is the road itself.
Okay.
Okay. That's a force there that's turning the car. If you are in an airplane, you are banking on a cushion of air as you complete your turn. Mm-hmm. If you're in space, there is no force doing that. So if you're in space, you just have to fire rockets.
Right.
And so they don't tip and turn. It looks cool when the TIE fighters did that in Star Wars and
Right.
and the Millennium Falcon. You know, it looks cool, but that's not how it would happen. You just have the rockets change the direction that it turns in.
So all of those maneuvers that you see the Millennium Falcon make when in
Yeah,
space,
the maneuvers they're atmospheric maneuvers. They're not vacuum.
None of
maneuvers.
that means anything.
Right.
It's
right.
yeah. Wow.
Plus, didn't they at the end of the Star Wars Episode 4 when they had when they were celebrated for destroying
The Death Star.
the Death Star, didn't they just fly in from an open bay exposed to the vacuum of space, and then they just get out and walk around?
Yes.
I see.
But I think there's a force shield that holds the atmosphere inside the ship, though.
Well, you just made that up right now.
No, I'm serious. That's
Okay.
Yeah, no, I'm
Okay.
serious. I think that's how it works. There's a
Okay,
force
magic
shield that
force
holds-
fields. Okay,
Yes,
fine.
I mean, but seriously, there's nothing in Star Wars that's scientific. Let's be honest. I mean, seriously, there's
You know what the
absolute-
least believable thing to me was? Here are the fighters coming in, and there's the guy with the traffic cones directing.
Yes,
It's
they
like
still right.
you don't have a better way to do this in the
Yeah.
25th century or whenever the hell this thing takes place.
And the other thing is too, they all fly in, and nobody fires retro rockets.
Oh, they just slow down.
They just
yeah.
slow down. Like in
Yeah,
Star Trek, though, when you fly into a shuttle bay, there is a kind of like a tractor beam that grabs you, and then you come in, and that's how
Yeah,
you
correct,
stop.
correct. Because Star Trek thinks about science.
Yeah, but Star Wars, they're just like, coming in. I'm coming in hot.
All right, so this is Airplane Banking 101, Jack.
Well, that's cool, actually.
All right, this has been an explainer jamboree. Stuff you thought you knew in 3 segments. And so I hope you like these, Chuck, because I bend your ear on them.
I love them. They're great. I mean, and I actually do learn stuff. And I got to tell you, man, it's great information to have at a cocktail party.
Okay. Because you'd otherwise just be completely boring at a
Exactly.
I got to pull out a nihilism here. Just
Exactly. It's like, you should go talk to that guy. I thought he was a stupid comedian, but God, he's brilliant. Guy is brilliant.
a stupid comedian. What kind of stuff? So, Chuck, we got to call it quits there. But this has been fun. I'm glad to teach you a couple of things.
Yeah.
I'm an educator, and I feel like I have purpose in life, and that I'm somehow fulfilling that purpose if I get you to learn something. Because you're a smart guy, and you know a lot. Well, so it's a challenge for me to find things that you might not know, really. I'm just letting you know that.
Well, there you go. That's I don't think it's much of a challenge, but I'll accept that as a compliment.
So another stuff you thought you knew on StarTalk. This is Neil deGrasse Tyson, as always.